friction.
Okay, here's the next sample problem for friction problems. And basically these are I think they're roughly gonna get harder throughout the week. So I'm gonna be doing more complex problems, which might help you with the more complex problems on your problem set. And they're also gonna try to cover different aspects or different types of problems related to friction. I'm not gonna cover any problems that are not related to friction because I already did a bunch of those last week. Okay, next problem. A 250 kilogram box slides down a ramp and then across a level floor. Let me draw that. So we have a ramp and then a level floor. Block. This is a 250 kilogram giant box full of weights or something. Somebody's delivering barbells to a gym. So it comes down here and then it later on slides across the floor. So the coefficient of kinetic friction acting on the floor here, mu k equals 0.2. So a person sees the box moving at 1 meter per second left. Ugh, I drew this wrong. I drew it. This is confusing. I'm going to redraw it. Sorry. I don't want to have to switch it in my brain. I want to switch it on paper. This is why you always read the question fully before drawing the diagram. I'm not very good at that. I'm very impatient. 250 kilograms comes down the ramp. Later on, moves to the left. All right. A person sees the box moving at 1 meter per second to the left and pushes on it with a horizontal force of 140 newtons to the right. So let's draw a free body diagram. So we have Fg, Fn. These are equal. We have a person pushing on the box. That's the applied force, and that is 140 newtons. There's no other force. Yes, the box is moving to the left, but there's no force acting on it in that direction. It's moving that way because of the ramp from before, but right now it's going to be slowing down because the person's pushing on it to slow it down. So the change in velocity is in that direction, even though the actual velocity is to the left, the change in velocity is to the right. Okay, so part A says, how far does the box travel before coming to rest? So this is a kinematics problem. We're looking for D. Technically, we're looking for the magnitude of displacement. We know the initial velocity, which is 1 meter per second to the left. And we know the final velocity is 0 meters per second. And we need to know one more thing, because remember in kinematics problems, you need 3 quantities to solve for the 4th. So you're probably getting used to, hopefully you're getting used to this by now, but when it comes to dynamics problems, usually you can use the free body diagram to figure out acceleration. That is the sort of crossover quantity that works for both, like you find acceleration in free body diagram calculations, but also in kinematics calculations. And it's the only one. Like distance and velocity and time, those aren't part of force calculations, and force and mass are not part of kinematics calculations. So acceleration is the thing that really links these two types of problems. So that's kind of a good way of thinking about these types of problems, is like how do you translate a force problem into a kinematics problem? Well, it's through acceleration. It's the only sort of conversion. Okay, so anyway, we need to find the acceleration here. So in order to do that, we know the net force. Well, no, we don't know the net force, because you know what? I made a mistake. Let me go back to this diagram. This is not the only force, as a matter of fact. There's also the frictional force. I completely forgot. Why did I forget about the frictional force? Come on. This whole thing is about friction. So we have the frictional force, which is also acting to the right because it's opposing the direction of motion of the box. And we don't know how big the frictional force is, but we do know the mass and we do know the coefficient of friction. So we should be able to figure out this frictional force. Okay, frictional force equals mu times Fn, which is 0.2 times mass times gravity, which is 250 times 9.8. 250 times 0.2 times 9.8, 490 newtons. F net. We've got two forces both acting in the same direction, so 490 plus 140 equals 630. So therefore acceleration equals F net over mass. So that is 630 divided by 250, which is 2.52 meters per second squared to the right. All right, and let's come up here now. And so now we can use a kinematics formula. We know VI, VF, and A, and we're looking for D. So that would lead us to the formula VF squared minus VI squared equals 2AD. Okay, so 0 squared minus 1 squared equals 2 times, okay, this is going to need to be negative 2.52 because I put the 1 is positive, and so we're implicitly defining left to be the positive direction, but acceleration is towards the right, so I'm going to need to make this negative. So then times d. Okay, so negative 1 equals, this is going to be a negative 5.04 times d, and then just divide them. So forget about the negatives. 1 divided by 5.04. Okay, so we have about 0.2 meters to the left. Part B, how will the results change if the box is moving to the right and the person still pushes to the right with the same force? Okay, so now, let's see if I can squeeze this one in on this little section of page. Okay, so we've got normal force and force of gravity. Now the box is moving to the right at, let's presume it's at 1 meter per second. Now we've got the applied force, which is 140 newtons, but the frictional force is going the other way. And that is the same, 490. Okay, so now these two forces are acting in opposite directions, so the net force is going to be different. So the F net, 490 minus 140 is 350 newtons to the left. So the frictional force, wait, what am I talking about? The acceleration is the net force divided by mass. It's 350 divided by 250, 1.4. 1.4 meters per second squared, and that is to the left. And so going back to the same formula, now, so VF is still 0, VI, is still 1, but the acceleration is now lower because the forces are acting in different directions instead of like combining with each other. Okay, so negative 1 equals negative 2.8 d, so d equals 0.36 meters to the right. And it travels farther this time than it did in the first question, which makes sense because the person is actually trying to keep it moving. So it's actually helping the box travel farther rather than trying to stop it.